In this video, we will talk about how to find half-life or doubling time. We already wrote down the doubling time formula on page 2, and that was doubling time t is equal to natural log of 2 divided by the rate r. And half-life formula is exactly the same. And not exactly the same. We're going to use half instead of 2. But let's try to set up one and then come up with that half-life formula. But this is from a previous work. We have that. All right, so now it looks like we're using the same equation, but the notation is a little bit different. Remember we used to have A equals the initial value p times e raised to the RT power, right? So even though the formula that they have on this page looks a little bit different, it's really the same thing. A, the ending amount, they're using a variable y, okay? Like there's an output of a function. And for p, the initial amount, look at the notation. They use y naught, okay? And how did I just read that? This is y naught. Or y sub 0, okay? Which means, okay, the amount at time t equals 0, okay? So that is really the initial value, the amount at time equals 0 or the initial amount. I think that was the only different notation. Otherwise, it's really the same thing. Now take a look. When r is bigger than 0, when r is positive, we're looking at a growth function. When r is a negative, when the rate is negative, we're looking at a decay function. So let's take a look. A radioactive substance decays according... Now look, because they said this is a decay function, take a look at that rate. The rate r is a negative, right? The radioactive substance decays according to the following function, where y sub 0 or y naught is the initial amount present and y is the amount present at the time t, in days. Find the half-life of the substance. Round your answer to the nearest tenth. I'm gonna, instead of coming up with the half-life, or using the half-life formula, I didn't give that to you just yet. I'm gonna just set it up and solve for it, and we'll see what the half-life formula looks like. So I will say y sub 0 is 1. Let's say that we have 1 gram of this substance. Half of that is just 1/2, right? So I'm going to set y sub 0 equals 1 and y equals half. And I'm going to solve that. So on the left side, let me put half. On the right side, I will put 1 times e raised to the negative 0.0936t. Look, if I divide both sides by 1, and we know it, we don't really need to, right? We will get half equals e to the negative 0.0936t. Okay, guess what we're going to do now? We're going to take natural log of both sides. So let me have some room here. I'll take natural log of half on the left side, and I'll take natural log of e to the negative 0.0936t power. So what will happen? The left-hand side is natural log of half. The right-hand side, the exponent of negative 0.0936t comes down, right? This will come down to the front, and natural log of e will just turn into 1. Now, last step is to divide both sides by that rate of 0.0936. Divide both sides by negative 0.0936. Okay, so here is the half-life. Half-life t is natural log of half divided by the rate of negative 0.0936. And they want us to answer this to the nearest tenth. So this is where we have to go to the scientific calculator and type in natural log of 1/2, and that is getting divided by negative 0.09 36. Look, the half-life is approximately 7.4, and I'm looking at the unit. T is in days. So half-life is 7.4 days. So if we give this substance, radioactive substance, 7.4 days, it will become half of what it started from, okay? So here's the half-life formula, and you probably noticed it. Half-life formula is natural log of 1/2. So remember, for doubling time, we used natural log of 2, right? We're going to divide that by r. But r is going to be a negative number because when we look at half-life, we're looking at a decaying function. So you can now go ahead and use that half-life formula from now on. I think I'm going to use that for the last example here. So a mass of a radioactive substance follows a continuous exponential decay model with the decay parameter of r equals, r equals 0. Oh, hold on a second. Notice that they said decay factor. This will be wrong for me to say 0.085 because positive r means exponential growth, right? That's the growth. So what do I have to put in front of this number to make this a growth rate, a decay rate? I better put a negative in front of it. If I don't put a negative in front of it, my answer will have the wrong sign. But, nothing that we will not be able to notice, but just to be sure, make sure the r is negative when you're doing a decay rate. Find the half-life of the substance. Now that's all we really need. So here's the half-life. Half-life T of the substance is natural log of half divided by the rate of r. So let's get the approximate decimal for this. See, once you have that formula, you really don't need to solve for it again because they're all going to be the same, 0.85. And that comes out to be about 8.2. And I have to double check the time unit. Is it in years, months, or days, or what? It says per day. So I will say it's going to take 8.2 days for this radioactive substance to become half of what it started from, okay? Half of the original amount. And that concludes lesson 3.6.